CMC Learning Center. Learn like a pro.
Chemistry math often presents as a chaotic swirl of guesswork, a collection of isolated formulas with no clear connection. We can replace that unpredictable mess with a rigid, mechanical system. Think of it as an industrial pipeline, where data goes in one end and the correct answer comes out the other. This is the universal six-step engine. By moving from the cyan inputs on the left to the gold outputs on the right, this framework solves stoichiometry problems through a repeatable sequence. Stoichiometry is the mathematics of the chemical recipe. It provides a rigid blueprint for taking raw data and pushing it through one unbreakable pipeline. This image shows our first case study. On the left, we have a crucible containing magnesium carbonate, which decomposes into magnesium oxide and carbon dioxide gas when heated. Our starting data is exactly 8.4 grams of solid magnesium carbonate. Our target is to calculate the precise mass of the newly formed magnesium oxide. We will predict a physical mass that does not yet exist, using only our starting weight of 8.4 grams and the rules of the engine. We load our raw data into the starting chamber of the pipeline, in this case, the 8.4 grams of magnesium carbonate. One common error is the gram-to-gram trap. You cannot convert the mass of one substance directly into the mass of another. The relationship between chemicals is not based on mass alone. This is the golden rule of the engine. The pipeline will physically reject grams. To cross the gap from your given substance to your target substance, data must be converted into a counting unit called moles. We divide our starting 8.4 grams by the molar mass of magnesium carbonate, 84 grams per mole. This calculation converts our given data into 0.1 moles. Converting to the mole unit provides the power to drive the rest of the engine. This conversion is the mandatory first step for translating one physical material into another. In step 3, we load the chemical equation. This serves as the reaction's required blueprint. The engine requires a balanced equation before it can proceed. This is a mandatory checkpoint to ensure there are equal numbers of each atom on both sides of the reaction. Once balanced, we move to step 4. We extract the molar ratio directly from the coefficients. Because no numbers are written here, the coefficient is 1. The ratio between given and caudate is exactly 1 to 1. This molar ratio functions as the transmission gear for the pipeline. It dictates exactly how much product will yield from our specific input. Step 5 applies the 1-to-1 ratio. Since the ratio is equal, our 0.1 moles of starting material translates exactly into 0.1 moles of our target, magnesium oxide. The color shift in the diagram indicates we have crossed the bridge. We are now operating entirely in the target substance's territory. Step 6 is the final resolution. The system has 0.1 moles of magnesium oxide, but requires a physical output in grams. We multiply our 0.1 moles by the molar mass of magnesium oxide, 40 grams per mole. This yields exactly 4 grams. The engine has successfully transmuted our initial mass input into a perfectly accurate and physically verifiable mass output. Here is the complete unbroken journey. We fed 8.4 grams in on the left, applied the balanced equation in the center, and received a 4-gram output on the right. This structured approach applies to more than just simple solid-to-solid reactions. The stoichiometry matrix shows that even if inputs change to liters of gas, or the ratio shifts to 1 to 3, the foundational 6-step architecture remains the same. Across all varying examples, the center protocol, crossing the mole bridge via the balanced ratio, is the absolute constant. Move away from treating chemistry math as a guessing game. Balance the chemical blueprint, follow the pipeline, and trust the engine.